So if you took a physics class in high school, you probably talked a lot about Newtonian mechanics or classical mechanics. Well, on Earth, that works pretty well for most applications, but then Einstein came along and kind of turned all of that on its head with his theory of relativity. So in this example right here, I want to talk about something which just seems crazy. So if you take, for example, a rocket ship, and you were to try to place that rocket ship in this house, notice it's a little too big to fit in the house. Well, according to Einstein's theory of relativity, length contracts the faster things move. So for example, if this rocket were moving at the speed of light, or close to it, its length would contract enough to actually fit in the house when it hadn't fit in the house previously, not going at that speed. So Einstein's theories of relativity may seem a little far-fetched, but we actually have a lot of evidence that these theories are pretty sound. In this video, we're going to investigate Einstein, his theories of relativity, and talk a little bit more about how a rocket that couldn't fit previously into a house could fit if it was going fast enough. Let's get started. So I mentioned Albert Einstein really changed a lot. And a little bit about Einstein. He was born in 1879, lived to about 1955, and born in Germany. And he was a theoretical physicist. So he was very concerned with the theory behind how physics works. In 1905, he published his theory of special relativity and then published a few versions, but finally gave a final version of his theory of general relativity in 1916. So in this video, we're going to look at the difference between special and general relativity and look at some of its applications. So speaking of general versus special relativity. So I want you to think of two different sides of the same kind of coin. When we're talking about relativity, Einstein proposed this idea of general relativity, which really has a lot to do with gravity and gravitation, right? So in this exact instance here of this picture, you're actually seeing some massive galaxies and stars being pulled by the gravitational pull from some of these galaxies and the planets. So we think of the Earth, right, on the Earth, gravity, you drop something, right, it falls to the ground, and, that's just gravity on our Earth. But actually, what Einstein proposed is very different about gravity and why we have gravity. Then special relativity is his theory on the structure of space-time. Notice I didn't say space and time, I said space-time, because he had this idea, as we'll explore a little more, that everything's relative because of the bending of this space-time, okay? So general relativity, a little more about gravitation, special relativity, specifically about space-time. So let's get a little more in depth into special relativity. There are really two main ideas that fall in the category of special relativity. The first one is the principle of relativity. Basically, everything is relative. Before then, we sort of thought as everything kind of being a fixed frame, right? A frame of reference that was kind of fixed, and you were to the left or the right, or time was before or after. There was a fixed frame. Well, according to Einstein, it's actually all relative to the reference frame. So take, for example, these two images. So down here we have an observer watching this train. And let's say this train's moving along at, 20 meters per second. If there are some kids on that train and they throw the ball, let's say she throws it with a force of 5 meters per second this way. Now we have the 20 plus the 5 to this reference person here. Now the ball's kind of going 25. But because they're on the train that's moving, this ball moving in this direction is relative to them. So it's really only going 5 meters per second in that direction, okay, to them, but to this observer. So once again, it depends on the observer and the reference frame. So it's all relative. So the second idea has to do with the speed of light. So we all know, right, light travels fast. And his second principle is that the speed of light in a vacuum is actually the same for all observers, regardless of their motion towards the source of the light. So in a way, we're talking here, it's all relative to a reference frame. Here he's saying, well, the speed of light is actually the same for all observers, okay? And that gives us the famous equation equals mc squared, which I'll talk about more. So let's get into this idea of the speed of light a little faster, right? Here we have light going to the moon pretty quickly, right? Light from the moon, light from the Earth to the moon traveling pretty quickly, speed of light. So we have calculated that the speed of light is actually 299,792,000 meters per second. If you are in the United States and you need that converted, well, that's actually 186,000 miles per second. That is how fast light is moving. Now, in Einstein's famous equation, E equals mc squared, the c is the speed of light. M is the mass of an object. E is the energy from that. So he's proposing that objects of mass have energy and it's relative to the speed of light. Okay, so you may have also heard this term, a light year. A light year is actually not a time, but a measurement of distance. In other words, a light year is the distance that light travels in 1 year. So a light year is actually, let's see if I can get this right, 5,900,000,000,000,000 miles. That's how many miles light can travel in a year. So when we say something so many light years away, we're not saying that's how many years it takes to get there. We're saying that's how far distance it is actually away from us. So think about our source of light on the Earth. Our source of light is the sun, which happens to be about 150 million kilometers away. On average, sunlight takes about 8 minutes and 17 seconds to travel from the sun to the Earth. So the crazy thing is, if the sun exploded randomly, right, it's not going to happen. But if it did, we probably wouldn't know until 8 minutes later, right? Because it takes 8 minutes for light to get from the sun to the Earth. And even crazier than that to me is this idea that some stars and galaxies are so far away that when the light from those galaxies finally makes it to our eyeballs, what we're seeing is something that happened billions of years ago. So in a way, we're looking back in time because the light has taken that long to actually reach us. So in a way, we're looking back in time. So another really interesting point of special relativity is this idea of time dilation. Time, according to Einstein, will pass more slowly for someone traveling at the speed of light relative to someone standing still. If you watched the movie Interstellar, this was involved in that movie, that people that were getting close to the black hole were actually, time was moving different, right? So if you are on the Earth, for example, and you're observing, and a rocket ship flies around, and let's say it's going close to the speed of light. If that rocket ship goes around some galaxies and comes back, and you're on that rocket ship, because you're traveling close to the speed of light, your time is dilated. Meaning, if time is on the Earth is passing very fast, it would be about 60 years. Let's say you took a 60-year trip for people on the Earth. Well, for you, if you're moving close to the speed of light, because time dilates and moves so slowly, your time passed would only be 3 years. So this is crazy to think about. If you got on a spaceship moving close to the speed of light, were gone for 60 years from the Earth's observers, you came back, you would have only aged 3 years. They would have aged 60 years, okay? Because time dilates. It's all relative, thus theory of relativity. As I started the video, we also talk about length contraction with special relativity. Objects appear shorter the faster they're moving in relation to the observer. So once again, let's go and let's talk about a spaceship. If you're the astronaut on a spaceship, and on that spaceship, you can walk around a bit. Let's say it's 100 feet long, right? To you, on the spaceship, it's 100 feet long. If you are traveling on that spaceship at, let's say, half the speed of light, to an observer watching that happen, the spaceship appears to be only about 87 feet long. The closer you get to the speed of light, let's say 95% of the speed of light, then that will shorten even more because length contracts relative to the observer. So once again, we see some crazy things happening here the closer we get to the speed of light. Now, do we have any rockets today that can get close to that? Of course not. But as I'll show you in a moment, we do have some things that do get close to that. Okay, so let's move from special relativity to general relativity. So you may remember general relativity is really more concerned with gravity. So general relativity says that massive objects deform space and time, or space-time. Thus, gravity is not a force, but the curvature of space-time caused by unequal distribution of masses. And I've used this example many before in some of my other videos, but massively large objects like the Earth, the Sun, especially like a black hole, actually bend space and time. And my example I'm going to use again is a trampoline. If you are a person sitting in the middle of the trampoline and you put some object here, it's going to roll towards the center. Imagine that space-time is sort of like a fabric of a trampoline, and this object is bending that so things naturally move towards that massive object. That is what creates gravity according to general relativity. So these masses then will move along what we call geodesic lines. And so I've sort of mapped out like some geodesic lines. Basically, it's just the quickest way to get from point A to point B. So geodesic lines then are what are going to be bent here and move these masses along them. So this gets very complicated, and I'm not going to go into all this, but Einstein tried to come up with some equations. His field equations really attempt to describe how that matter is affected by the curving of space-time. And here you see what's called a Schwarzschild metric, which is an attempt to say this massive object here, this is the way, this is the geometry, this is the math that actually folds space-time. If it is a spherical, in this case uncharged, non-rotating object, which we don't have many of those. So this is really just an example, an illustration. If you look at Einstein's field equations, I recommend go online, Google these. They are very complex, and they're a way of trying to describe the math of how our objects bend space-time. Really fascinating to dig deep into, but fair warning, you're going to need some advanced calculus, some advanced differential equations to really look at that. All right, so then this general relativity is also concerned with gravitational waves. So what we know, what we observe, is that rays of light bend in a gravitational field. So gravity can actually cause light to bend. If you watched my video on black holes, I talked about how the massive force or the massive attraction of the black hole actually bends the light and the light can't escape. Well, large objects actually are bent by gravitational fields, right? So these large objects have these massive gravitational fields, bend light. Then general relativity is going to predict the path that light will follow, and then it will follow the curvature of space-time as it passes near a star. Well, what does this mean? Well, what this actually means is that people that are astrophysicists or people studying space can actually use this knowledge and can measure the shift in the light waves because of gravity and predict some things. In fact, you may have heard a lot of measurement of the redshift or measurement of redshift dilation. And that's just about what they're doing is they're trying to determine what's going on there in space by how much the shift of this red light of the spectrum is actually occurring. Okay, so how do we know this? Is this just science fiction? Is this just a movie? Well, actually, no, we have really strong evidence that really support Einstein's theory because we can actually use particle accelerators in experiments to accelerate protons and electrons at near the speed of light, right? We as humans can't do that right now. Spaceships can't do that. But if we take these particle accelerators and accelerate particles, protons and electrons, near the speed of light, we can observe some really fascinating things by having very precise measurement devices. And so how a particle accelerator works here is basically we have these charges going back and forth, right? This voltage is then moving these particles very, very fast, and we can accelerate them. Well, if we're moving particles at the speed of light, we've got to have a pretty big accelerator. So as you can see here, this is actually the Tevatron accelerator at Fermi National Lab. This was shut down in 2007, but you can see that these particles are actually just accelerated around these big loops, and that is actually how we get things moving so fast, because we have this big distance over time. It can move faster and faster, and then we can measure it. The largest accelerator right now is the one at CERN, which is pretty close to Geneva. And what we see is that if you sort of look here at the map, this is actually the 17 miles around that this large hadron collider there at CERN in Switzerland is actually measuring. And here's sort of a picture of some of the electronics and all of the experimental tools and measurement devices that are linked to that accelerator. So this massive undertaking by the scientific community in Europe has really opened our eyes to a lot of really interesting things going on with relativity. All right, so let's talk some real-life applications of this. Something you use probably every day, maybe, is GPS, right? So you got GPS on your phone. All right, I got it on my watch. A lot of people have it in their cars. So GPS, Global Positioning System satellites, actually work because it sends a beam up to a satellite and that beam comes back. Well, these satellites and GPS actually have to account for relativity, the bending of space-time in these gravitational waves, or they would be incorrect and they would be saying, okay, turn now, but you actually would be way off. So because an observer on the ground, right, us on the ground, looking up, we see satellites in motion, but that's relative to us. They're actually moving, and because they're moving and it's relative to us, we would think their clocks are actually ticking more slowly. Think right about my example with astronauts leaving and going around, right? Their time is ticking more slowly. So if the clocks on the satellite are kind of ticking more slowly than our clocks here, we got to adjust for that with special relativity. Another example, and this doesn't, I don't know that this technically relates to Einstein's theory of relativity, but it may help you understand this sort of length dilation thing a bit. When you're driving down the road and you've got these lines in the center, when you go by them, they may seem pretty short, but have you actually gone out and measured the length of one, right? Some of these are several meters long, right? If I were to ask you to guess, how long do you think that is? You might say, a foot or two. But notice this relative position. Here, looking at this position from this reference point, these look pretty small. But when we look at the lines in the road, notice they're actually quite long. I'm not advising that you go out and stand in a highway and measure the length of these lines, but if you did, you would find they're actually several meters long in some cases. Okay, so Einstein's theory of relativity. It can get complicated, but hopefully this video helped you understand the basics of length dilation, time dilation, gravitational fields, because as Einstein said, it's all relative.